Thank you, everybody, for joining the now 5th annual 2025 Web Science Digital Libraries Research Group Expo. And this is an opportunity for the graduate students in our research group to share their current research and give an idea of what they're doing, where they're going, and just an excuse to bring us all together, including various alumni and prospective members as well. So we always start with a introduction from the faculty, and I'll go first. So I'm Michael Nelson. I'm a professor of computer science here. Also have a joint appointment at VMask, and I'm the deputy director of the School of Data Science. So I've been here a really long time. And if you know me, you know I won't shut up about web archiving and disinformation in web archiving, social media, and all of these things. So it's great to see some familiar faces here. Very happy they can join us. All right. Dr. Weigel, you want to go next?
Sure. Hi, I'm Michelle Weigel. Professor, have also been here a very long time now. And I am the GPD for the PhD program and also serve as associate chair for graduate programs and research in the department. And, I do web archiving, social media, but I also have a huge interest in information visualization. So I'll be critiquing everybody's charts that they're presenting today. Just kidding. But in my head. I teach the two InfoViz courses that we have here in the department.
Okay, excellent. Dr. Wu, I know maybe you have to step out. You want to?
No, I'm good. Yeah, I just finished
Okay.
the PI meeting. So,
All right, excellent.
Okay. Hello, everybody. My name is Jhon Wu. I'm currently assistant professor of computer science to be promoted as associate professor effective in July. Thank you. My research interests are natural language processing, scholarly big data, information retrieval, the digital libraries, and the science of science. I have supervised 7 PhD students, including a co-advised student. I've graduated 1 student, Montebeer. I think he's going to attend the commencement this week. And so my teaching has been focused on several classes on web programming, the database concept, and recently on information retrieval, deep learning, and foundation models. Okay, that's me. Thank you.
All right, excellent. Thank you. Dr. Jayarathna, calling in from NASA Langley, maybe?
Yes. So I realized that the NASA network can disable the camera, so I can't open my camera for some reason. I think that may be the reason. But I'm Sampath Jayarathna. I'm an associate professor of computer science, and also I'm part of the School of Data Science. Right now I'm on sabbatical at NASA Langley, working at the integrated systems group over the summer and until I'll say until August 3rd or something like that. My area of research is in eye tracking, AR, VR, and drones. I have, over the past, I would say, 6 years, I graduated 3 students. I can see Gavin they joined from UT Austin. She's a postdoc over there. Yasit and Bathsheba, and I have 4 current students at this point. Banika is ready to graduate as well. That's all from me. Thanks.
All right, excellent. Thank you, Dr. Ashok.
Hello, I'm Vikas Ashok. I'm an assistant professor in the Department of Computer Science. I joined in 2019. And my area of research is human-centered AI with a specific focus on accessible computing. So essentially, I look at the latest NLP, computer vision techniques, and see how I can build systems using those techniques to help people with visual disabilities interact with computer applications and smartphones. anything. I think that's it.
All right, excellent. Let's see, Dr. Porstar. Are you there?
You saw her.
Yeah. Let's see.
Yeah, the
Oh.
microphone.
Yep, there she is. There she is. We can't hear you.
Mic seems to be on.
Still can't hear you. We can see you. So between Drs. Jairatna and Drs. Porstar, we have a complete Zoom experience. Yes, it was low, but keep turning up whatever you're turning up.
Okay, how
That's
about now?
better. Got you now. Got you.
Okay, so hi everyone, I'm Faryana Porsardar. I'm research assistant professor at VMask and School of Data Science. My research interests are in the area of social computing, generative AI, machine learning, and web archive. And so I've joined ODU in 2020. I was on campus at computer science. And then 2 years ago, I came to VMask. So I'm glad to see you all here, and I'm excited to hear about all of your research. Thank you.
All right, excellent. And let's see. So I know I put Alumni Minute Madness at the end, and we'll come back to that. But Chuck, since you're here, you want to tell us what you've been up to? First, introduce yourself to everyone who might not know who you are and the record that you hold.
Oh dear. Okay. By way of introduction, I am a graduate of the WSDL group in 2014, I believe. The record I think you're referring to, the last time I was on campus and I popped into the WSDL office, it was still sitting on your desk, Michael.
Oh, yes, of course.
Oh, yeah. For those of you who have wandered into that cave, that dissertation that's sitting on the table is mine. After graduating, I started teaching. I'm still doing it. I'm teaching over at TCC, a community college here in Southeastern Virginia. I teach at ODU some computer science and some engineering management courses. And I have a couple cats. And I am just enjoying life and looking forward to seeing what everybody's is working on and how the state of the art has progressed. Looking forward to it.
All right, excellent. And let me see, I'm not sure I see any other alumni, but if I'm somehow missing you, please give a shout. All right. Let's see. So the format that we're going to use is we normally have like a 20-minute slot for the presentation, really aiming for about 15 minutes of presentation and 5 minutes of question and answer. Again, this is really meant to be information exchange. So please ask questions. Please learn what your fellow students and research professors are doing, what they've been up to, so we can hopefully continue to collaborate. All right, and so I'm going to stop sharing, and the first up is Kritika Garg, and you should be able to share your screen. All right, got it.
Awesome.
All right, whenever you're ready.
Is it fine if I keep it in this?
I'd really rather you put it in slideshow.
What else?
Thank you.
I think it, oh, it's still visible.
Please go back to slideshow. There you go. Okay.
Sorry, it's having some trouble when I put it in slideshow on my end. Don't know what's
Okay, if you can't do slideshow, then, I mean, do what you can do. Okay, we are ready at any time. Okay,
okay.
please begin.
Yes. Sorry about that. Hello, everyone. I'm Kritika Garg. I will be presenting our work, Not Here, Go There, analyzing redirection pattern on the web. So did you know that Facebook used to be an employee phone book directory in 2000? Very different from the large social media network we know it as today. So even though the URL remained the same, facebook.com, the identity is completely different. Then we have this example here where our ODU computer science department website has changed its URL multiple times. So over the years, many web pages disappear or change their content, change their location. For example, for our department website, it used to be cs.odu.edu, then it was comp sci, and now it's computer science. So if we curl to it, we can see it. In browser, it's seamless. It's hard to notice the redirection, but if we curl to it, we can see it takes us to redirection or to hops to reach to that target URI. So we started by curating a data set of 27.3 million URIs by sampling around 1 million URI every year of IA from 1996 to 2021 to study web evolution and content change. The work I'm presenting today is part of this project. We then crawled these 27 million URLs to see their status, whether they were alive or dead, how they were terminating. And then we found that 40% of these were, which is 11 million, were redirecting. So this prompted us to further study these redirections and to analyze their patterns. We crawl these 11 million URIs using IA's Heritrix crawler, following up to 10 hops. As you can see in this image, we started with around 11 million redirects. Majority of them terminated after first hop. And 3 million went further. Then 2 million of those ended with 2 hops, and 672,000 went further. And only like 0.42% of these redirects exceeded 4 hops. So it indicates that 5 hop limits are generally sufficient for crawling redirects. So the crawl result for us was that 50% of these were successful, while rest of them resulted in errors. and like teeny tiny percent were still, like 0.06% were still exceeding 10 hops. So this graph here shows us the same, but we can see the percentage of each individual error here. We noticed that 13.2% of these error did not had any terminating status code. On further observation, we saw these were sort of invalid redirects without location header, relying instead on HTML-based redirection, like our first example here. Or it was a redirect with an invalid location header, as we can see here. After removing these, we identified how many redirects were canonical and non-canonical. So canonical redirects are refer to redirecting multiple URIs to a single authoritative, like one canonical URI. For example, we have HTTP blog.nasa.gov redirecting to its HTTPS version. We converted our source and target URI in cert format. The cert format is a normalized URI format of IA that restructure URI by reversing the domain order and stripping protocol and port number to make it easier to group and compare similar URIs. So in our case, if the source and target URI was same, we marked it as canonical, and if it was different, we knew it was redirecting to a new location completely, so we marked it as non-canonical. So we had 6 million of these canonical redirects. We looked at the different types and their prevalence. Most of these were HTTP to HTTPS redirects, which shows the reflect a push towards secure web practices. We also saw that 48% of them terminated successfully. However, a large portion of them terminated in errors, which highlight the potential issues such as link rot, outdated URIs, improper or server instability. Then coming to the rest, 3.5 million non-canonical redirects, we looked at the different types and their prevalence again. 65% of these non-canonical redirects involve domain change, which sort of indicate that there might be a risk of like content drift or security issues. We also looked at the impact of URL change on the path depth, and we observed that these non-canonical redirects often preserved or simplified, prefer simplified path depth. For example, here we have an example here where the domain is altered, but the rest is kept the same. Then redirects, we also have redirects to deeper path, which usually guides users to a specific or updated resources. Like in case of URL shortener, a short URL is redirected to the larger one, as we all know. And then here we have examples of like redirecting to a shallower path depth. So we observed that it was often to simplify sites by consolidating or removing the old content. So often this was linked to like loss in content. And here we can see that 73% of these non-canonical redirects terminated with 200 OK. However, a 200 OK doesn't really guarantee the original content still exists. This redirect may lead to root pages, spark domains, or soft error pages. So this can mislead users and search engine crawlers, affecting content preservation and indexing. We found many cases where the original content was lost despite this being it being terminated as 200 OK. Like in case of syncs, some redirects end at popular target URI, which we are referring as syncs. For example, we have google.com here as one of the popular syncs. Here, the search engine web page sync function as general purpose landing page. So the traffic from these sites are redirected to this main home page. This usually suggests that original URIs are either outdated, broken, or no longer maintained. We have our top 15 syncs listed here. So for example, if I click here, one of them, yeah, we would get rickrolled. So we sort of got rickrolled while working on this ourselves. So some redirections lead to unexpected destination. We also saw other famous meme pages, redirects leading to meme pages. Okay, another common sync we have is a social media login page. As every article have these share buttons on them. And crawler, if the crawler is not logged in, it is generally redirected to the login page, leading to the login page getting crawled and archived multiple times, wasting the resources. Then another common sync we have is affiliate marketing syncs, where we have an example here. This came up as our topmost sync, where these small pharmaceutical sites were directing traffic to this site, offering discount to people. Similarly, we saw error syncs, and here the traffic was being redirected to the error page, to a common error page, after these sites that they hosted were no longer active. So this prompted us to identify how many other custom 404 error pages we have. We identified 62,000 custom error pages in our sample, and 47% of them were returning 200 OK. So yeah, soft 404s. 47% of them were soft 404s. And these are the other types of, like, all the types of syncs that we categorized based on what we observed. So to summarize, we analyzed 11 million URIs, 50% of them led to live pages, rest returned errors, and some exceeded the 10 hops limit we had. We also saw that 5 hop limit is sufficient for the crawler, since only 0.42% exceeded 4 hops. We found 6 million canonical redirects in our sample. Majority of them were HTTP to HTTPS. We saw a lot of them were returning errors. 3.5 million were non-canonical redirects. And we saw that they often preserve or simplified path depth. 65% of them involved domain changes, which could indicate the risk of content drift. We also looked at sync. and identified like login pages, Spark domains, and custom error pages as the frequent endpoints, and also sync serve as roles like affiliate links, pranks, but they waste scroll resources and obscure like real content. Then we have we looked at custom error 404 error pages and saw that 47% of them were soft 404s. So these insights that we documented in this work can help guide better redirection practices to improve web reliability, support content preservation, and inform future research. Thank you.
All right, excellent. Thank you. Any questions, comments for Kritika? Chuck, don't be bashful.
I have a question.
Okay.
So can Kritika tell me, so what's the motivation for this research? I'm sorry if I missed anything. So why are you interested in doing this analysis?
So we want to study about changes in URL, like about the web evolution in as whole. So we are looking at different ways. So this was like this is the part of like the bigger project that we are working on, where we are looking at lifespan of the web pages. So when we saw that 40% of our data was redirecting, that sort of prompted us to look further into redirection and how it will now we can better use this information to better guide us into like while we're looking into like how to define the lifespan of pages that are redirecting.
Okay, thank you.
All right, there you go, Chuck.
Kritika, could you pop to page 11, please?
Yeah.
There was something that caught my eye there that just caught my eye.
Yes.
Oh,
Was this the one?
yeah. And whatever it is, I don't see it now. My problem. Oh, and two other things. One, I like the Sankey plots. I think those are useful. I like that as a technique.
Okay.
And you were able to work in the word canonical more than once. And if you can get idempotent in there, you've got them all covered. Have fun with it.
Thank you.
So, Kritika, can you talk about pages that redirect, but not they redirect via the meta header in the HTML page itself, and not really an HTTP event? And can you estimate how frequent that would be and how this would impact our data set?
Sure. So we found like around 13% were could possibly be part like these
Yes.
redirects, the one with the meta headers,
Mm-hmm.
were like part of the 13% of our redirecting URIs. So so the crawlers couldn't follow them, and
So, I mean, I mean, do we know that we found them all? Because basically you have to go through and look at the HTML, right? 'Cause if
right. So
you just do a curl, the curl won't know to follow this, right? You need an interactive browser, Chrome or Firefox or something to actually follow this redirect.
right, and so we didn't really look into that data set, but just pick the handful of them in order to understand what was happening, why they were not getting followed up. But yeah, that we can use our interactive browser to look into that data set and see how many are actually not getting follow-up redirects because of this particular reason.
All right, but that seems expensive, right? It's much faster to go with curl or something like that, right? Do we have any idea what percentage that is? Did we do a small scale sampling?
That is something we haven't done, but that's something we can look into for sure. But
Okay.
yeah, it is a costly operation, so we can do it on a smaller sample.
Okay, excellent. Other questions, comments for Kritika? All right, if not, we'll move to our next presenter, and this will be Kumushini, who's calling in from the middle of the night in Sri Lanka, I believe. And we really appreciate you making the extra effort to join us.
Yes, thank you, Dr. Nelson. Let me
What
share
time is
my.
it there? What time is it?
It's almost 10
Okay.
p.m.
Okay. Thanks. So it's still today, though. It's not tomorrow.
Yeah. Hope I'm good with the slides.
Oh, good. Yep.
Hello, everyone. I'm Kumushini Thennakoon, a PhD student working in the NERDS lab and WSDL lab under the supervision of Dr. Sampath Jayaratnam. I'll be presenting our recent research beyond gaze overlap, analyzing joint visual attention dynamics using egocentric data. So first, I'll briefly introduce you what is joint visual attention. Simply, joint visual attention is a shared focus. So as you can see in this picture, the two people are looking at this book at the same time. And if we consider our area of interest as this page, so we can say that they are in joint visual attention at this moment. And this phenomenon is used by developmental psychologists to understand how children acquire language. And also, it can be used to identify conditions like autism spectrum disorder. And learning scientists are also using this joint visual attention, in shorter form JVA, to understand how small groups work together to measure the collaboration, the efficiency of the collaboration. Like that, they also use this phenomenon. So there are two types of indicators that we can use to identify JVA. One is behavioral indicators, and the other one is eye gaze indicators. So some examples for behavioral indicators are pointing with hand, gaze following, spontaneous looks to a social partner's face. For an example, in a parent-child interaction, if the parent is pointing their finger towards an object, and when the child is looking at the same object, at some point they tend to have joint visual attention. The eye gaze indicators, when it comes to the eye gaze indicators, now we have different eye tracking devices to track the gaze positions of two or more individuals. So if they locate their gaze positions in a specific or the same area of interest at the same time, we can say that they are in joint visual attention. Along with gaze positions, we also can use voice cues to better understand this phenomena when they are conversing with each other. They can gain joint visual attention through voice cues. To analyze this phenomenon or the joint visual attention, we can use two types of gaze metrics. One is traditional gaze metrics and the other one is advanced gaze metrics. Some examples for traditional gaze metrics are fixation count, fixation duration, saccade amplitude, and blink rate. But in this research study, our interest is towards advanced gaze metrics. Some of them are ambient focal attention with coefficient K, gaze transition entropy, low-high index of pupillary activity, real-time index of pupillary activity. Here, ambient focal attention with coefficient K is a metric that we use to understand the attention behavior of an individual. So if this K value is a positive value, we call it a focal attention behavior. And if this K value is a negative value, we call it a scanning attention behavior. So as a research group working on eye tracking data, we would like to look at this problem or look at this phenomenon actually using eye tracking technology. So with the popularity of wearable eye tracking devices, this wearable device is one of the most suitable device to use to identify joint visual attention. So in this study, we are using data collected from Project ARIA glasses launched by Meta. And these glasses are capable of collecting multimodal data, such as eye tracking data, voice data, and it also contains sensors like thermometer, barometer, and accelerometer, and etc. This pair of glasses contain 3 types of cameras. One to record the world, we call it world weave camera or the wearer's weave, and 2 cameras on both sides of the arms to record the weaver's peripheral weave, and 2 eye tracking cameras pointing towards the wearer's eyes to track the eye movements. And Meta also provide tools for data handling, data synchronization, data streaming, and visualization along with this Project ARIA glasses. So here I'll briefly discuss about the data set that we used. The data set is called ARIA Everyday Activities Dataset. It was curated by the same group working on Project ARIA glasses, and they curated this by recording different everyday activities using Project ARIA glasses. It contains everyday activities like cooking, making coffee, having conversations, etc. And it also contains recordings for single users and also for multiple users. Our interest is towards the recordings with activities involving 2 people. So this diagram shows the approach and the tools that we used in this research, and we divided it into 3 steps. In the first step, we acquired data for the activities where 2 participants are involved, and we downloaded the world view camera recording in MP4 format for both participants, and at the same time we downloaded the gaze data in the angle format for the both participants. From the MP4 files, we extracted frames and we saved them as frame sequences for both participants. And since we wanted to look at the gaze data in 2D, we converted the angular data into 2D position data as X and Y. Then we merged these 2 in order to create these gaze annotated frames. We projected the 2D gaze positions onto the extracted frames. In each frame, we have a gaze annotation. Then we considered a region of interest, an area around this gaze position as our region of interest, and we cropped that region, and we created 2 new sequences of the frames. from the original frames. I will discuss this first step with this diagram for the better understanding. Here we have, in the left side, we have two sequences of the frames for participant 1 and participant 2. In this red crosses shows the gaze annotation in this original video frame. And around this gaze annotation, we selected an area as the region of interest, and we cropped that region from each frame and created new two sets of frames. And here we considered both spatial and the temporal dimensions. So we call this one sequence a spatio-temporal tube. In the next step, since we have two sets of frame sequences, we input these two sequences or images into a convolutional neural network to obtain feature vectors. For each pair of images, we obtained feature vectors, and then we calculated the cosine similarity to check the similarity between these two images. We did that for all the images in both sequences. And after that, we manually inspected the similarity scores with the images, and we defined a similarity threshold so that we can filter the frames that are similar, that means which exceed the threshold. We filtered them as frames with joint visual attention, and we filtered out the rest of the frames. So in this image, I'm showing that how we calculate the similarity. For each time point, these two respective images, between these two respective images, we calculated the similarity score. We did this for all the frames in the two sequences. In the third step, now we have filtered the frames with moments of joint visual attention, and then we get the gaze data respective to these frames, and we input them into the RayMap API, which is Real-Time Advanced Eye Movement Analysis Pipeline, to calculate the advanced gaze measure coefficient K. After calculating coefficient K, we analyzed the dynamics of this coefficient K visually to understand the attention patterns. After filtering out, after filtering the frames with joint visual attention, we calculated the percentage of JVA by dividing the number of frames with JVA from the total number of frames. From this, we were able to understand that the activities with less movements, like walking and moving in between different activities, they have higher percentage of joint visual attention. Next, we segmented all the activities into 4 time epochs, and we annotated with the sub-activities inside each of these activities. This annotation helped us to understand the dynamics of the coefficient K, which I'm going to talk in this slide. So we calculated the mean K values in each of these time epochs. And by doing this, our main goal was to check whether if there is a specific pattern in this coefficient K fluctuations with low and high percentages of joint visual attention. we were able to identify some sort of a pattern when the joint visual attention is low, and another pattern when the joint visual attention is high. In activity 2, which is making coffee, we see that these coefficient K values are different for both participants throughout the activity time. So we categorize this as a asynchronous attention pattern since these are very divergent. And if we say the activity 5, which is watching television, we were able to see that these coefficient K values lie very closely throughout the activity. And there is a synchronous attention pattern in this activity. But at this point, we cannot actually come to a conclusion that this attention pattern solely refer to that joint visual attention. If it is low, we cannot really say that they have a synchronous attention pattern by only looking at 5 examples. But this is research in progress, and this is a preliminary findings. But we are planning to do extensive research in this part. With that, I will move on to the limitations and future work of this research. We identified 2 main limitations in this data set, which were like having body movements or movements of the participants. They negatively affected in identifying the joint visual attention frames, and also poor resolution and lighting conditions of these videos affected in calculating the similarity score. As future work, we are planning to further analyze the relationship between joint visual attention with coefficient K with a substantial data set. And also we are planning to incorporate other advanced gaze measures such as gaze transition entropy to further understand these gaze patterns and gaze shifts during collaborative activities. In summary, we can say that wearable eye tracking makes it convenient to study joint visual attention, and coefficient K, ambient visual attention coefficient K, can provide detailed insights into this phenomenon joint visual attention rather than only looking at gaze overlapping methods. And also this technique can be used to analyze collaborative activity in shared tasks. With that, I will conclude my presentation, and thank you for listening.
All right, excellent. Thank you. Questions, comments for Kumushini? So I'll go first. So I think it was slide 12, I think. So so we have things like watching on a phone and watching television. So this made me think, assuming everyone's wearing glasses, is there some scale feature here, right? So the form factor of a phone limits probably how many people can simultaneously watch this. But if it's a television, then everyone in the room, everyone in the family, whatever. If you're in a classroom, presumably, I mean, either everyone's focused on one or focused on 2 or 3 clusters. I'm wondering, is there some scaling function aside from the device, but like from the detection and handling as well?
Yeah, here we don't have something like that, but yeah, I agree with what you said about these devices attention, like how many people can join, but here we don't have any like scaling factor considered here. Just we calculated this based on only on that the frames we filtered as having joint visual attention. So the thing I wanted to highlight here was like in making coffee, people like go to the sink, take the kettle and do something like movements. There are very like more movements in those activities. But in watching television and watching a video on mobile phone, they are like stable, or they are like less moving in those kind of activities. So in those activities, it's kind of obvious that in those activities we have higher percentage of JVA, and with that, like we can come to an like idea when we are implementing this to any like a situation. So if it is a classroom kind of situation, we can use it. We can use this technique with less movements, like having less movements with the students, so we can get the most out of it. So that's what I wanted to highlight from this percentage calculation with these activities.
Right. So I was thinking like, imagine a doggy daycare situation where we have, 10, 20 dogs in a large area. We have, 4, 5, 6 humans. And so there are multiple targets to focus on. It isn't just a screen, right? But is there a way to and presumably people would hop between focus of activity. Anyway, I was just wondering, is there, some of these things sort of lend themselves to, all right, there's 2 people or there's 3 people or something like that, and that's all there'll ever be. But I was wondering if this could be extracted to larger groups of people, or perhaps even less structured environments.
Yeah, we can like extend this to a large number of people, but there's that limitation with like changing frames. So in a video with the changing frames, we have that limitation here. So at first, I selected 10 activities from the everyday activities dataset, and I had to remove 5 of them because of they were not having although there are multiple people involved in that activity, they don't have any joint visual attention moments in those activities because of their movements and all. So that's a limitation in this research. So it's very hard to identify the frames. Like we are only calculating the similarity between the frames here. But I think we can improve this by implementing like using some object detection, like really high level, like improved object detection model to detect the objects where the gaze is locating. So with that kind of update, I think we can extend this to a scenario that you explained.
Okay, thank you. Any other questions, comments for Kumushini?
I've got a couple.
Sure.
Kumushini, could you flip to slide 14, please?
Yes.
Okay, on this slide, you called attention to activity number 5 as being a synchronous attention pattern.
Yes.
Okay, when I look at activity 1, I see a similar type of shape to the curves. Would activity 1 be a synchronous attention pattern as well?
Yes, we can say that it is also a synchronous attention pattern by looking at it, but here I wanted to like, I highlighted the more synchronous here, but here also I have a few contrasting result as well. So even though the activity 3, if I say cooking and eating, it's having only 5.12, it's having a kind of synchronous pattern here. So that's what I explained, that by only looking at these 5 experiments, I cannot come to that conclusion, but we can see some kind of pattern in these synchronous patterns. Yeah.
on activity 1, that is sort of asynchronous, somehow I wrote the word collaborative down on that. For activity 1, playing the game, that was Connect 4 or something, right?
Yes.
Would it be different if it was a more complex game where the players were focused on their pieces rather than the opponents? Something like chess, perhaps? Would the pattern be different?
Yes, I think it will be different because, but in this approach, we selected that area of interest, not that the specific object. But if both of them are looking at the chessboard, we have that chessboard in our image. So sometimes it can lead us to a synchronous attention pattern. If we only look at the image similarity, but if we carefully look at the objects that they attend to, it can be different.
Okay, thank you.
Thank you so much.
All right. If there are no other questions for Kumushini, I think next up is Lamia.
Hi, Dr. Nelson. Can you see my screen?
Yep, got it. Thank you.
Okay. Hi, everyone. I'm Lamia Salsabil. I'm PhD student in the Department of Computer Science, and my advisor is Dr. Wu. So today I'm going to present our work, context-based ensemble classifier for open access dataset and software URLs in scholarly document. It's a collaborative work between ODU, Virginia Tech, and Internet Archive, and this work is funded by IMLS. So before I talk about our methodology and dataset that we have worked on, I would like to introduce some key concepts about computational reproducibility and OADS URL, which I'm going to use for the rest of my presentation. So computational reproducibility refers to the ability to reproduce research findings using the same data, computational methods, and experimental settings as the original study. And open access is a publishing model for scholarly communication that advocates for the unrestricted availability of research datasets and software. So the underlying concept is that the authors include URLs with the URLs of the research dataset and software in their scholarly publication with the intention of supporting reproducibility. However, the code and software may not be freely available in practice always. And OADS is the term that we have introduced in our research, which means open access dataset and software. OADS URL means URLs linking to open access dataset and software. Sorry. So these are a couple of examples of OADS URLs. So the first example is a URL that links to a dataset. The second one refers to a URL that is linking to a software. And the third one is the URL that links to both dataset and software. So as we know that open access kind of advocates for including research dataset and software in research publications, and it plays a key role in ensuring computational reproducibility. So nowadays, research institutions and funding agencies increasingly mandate sharing OADS in their scholarly publications to support computational reproducibility. So this open access dataset software are typically shared by URLs in scholarly publications. So the first step towards supporting computational reproducibility is the accurate identification of these URLs, and assessing the availability and preservation of such URLs will support the computational reproducibility. With the growing volume of scholarly publications, manual identification of such URLs is time-consuming and not scalable, because you have to go through those URLs, understand the context surrounding those URLs, to understand what type of resource that URL is linking to and who are the providers. So for the scalability, it is important to automate such process. But the key classification challenges is that URLs alone lack context. Let's say when we are looking into the URL, we cannot always say that whether this particular URL is linking to dataset software or to something else completely. So the context that is describing the URL it is necessary to understand that context to understand the nature of resource that URL is linking to. And sometimes the context describing such URLs can have complex semantics. Another key challenge is classifying across multiple dimensions. Let's say what type of resource is being linked to, whether it's a dataset, software, or something else, or it is linking to both dataset and software. And who is providing the resource, whether it's a third-party resource or whether it's created and maintained by the author itself. So the goal of our work is to automatically classify such URLs, OEDS URLs in scholarly publications by leveraging the context and expanded context of the URL. So for that purpose, in our work, we have created a benchmark dataset, which we are calling OEDS 1K. And this dataset includes about 1,129 manually annotated URLs and their context and expanded context extracted from about 1,574 scholarly documents in 15 domains. Then we developed a novel framework, Ensemble OEDS Classifier, which basically combines 3 different models to automatically classify URLs into dataset versus software to identify the resource provider, whether it's author hosted or it's a third-party source. And this model leverages the diverse model strengths for the performance. One of the models that we are using as part of our Ensemble OEDS classifier is a supervised contrastive learning model, which improves the Ensemble OEDS classifier's performance with the scarce data. So there has been some work on maintaining and preserving dataset and software resources. So one work by Markov Sev created a dataset of about 182,000 of GitHub repositories with at least 50 stars. Another work by Cosmo et al. Proposed software heritage for archiving source code from code hosting sites such as GitHub and PyPy. Another significant work by Eskemia et al. Highlighted the growing use of Git hosting platforms in scholarly publications and the need for archiving. And Michael Ferber also worked on analyzing code quality and usage on Git hosting platforms using external resources such as Microsoft Academic Graph. But however, none of this work focused on automatically distinguishing between the resource provided in the scholarly publications or the resource providers. So there has been a work by Suno Kake, who developed a cyber-based method to classify citations in scholarly papers, focusing on the resource roles, types, and citation reasons. However, they achieved a one score of a range from 70% to 78%, but lacked granularity in distinguishing the resource providers. So another work by Salsabil et al. That's our work, previous work, which in this work we proposed a hybrid model for classifying URLs in scholarly documents using supervised learning. So this work was basically a binary classifier that could only distinguish whether a particular link is a URL is linking to a dataset OEDS or not, but it couldn't either identify the resource types or the resource providers. So for our work, we have developed a benchmark dataset OEDS 1K, which includes about 1,129 manually annotated samples, which were collected from 1,574 scholarly documents. The source are Core 19 dataset and in-house corpus of electronic thesis and dissertations and archive papers. And the year ranges from 2016 to 2022, which covers about 15 disciplines. So from the figure, we can see the highest number of samples were extracted from biomedical and computer science disciplines. So in this dataset, each sample includes a URL, its context and expanded context that were extracted manually from the scholarly papers. That means the target sentence containing the URLs, the sentence that precedes that target sentence, and the sentence trailing that target sentence. So further, we have manually labeled those URLs into one of the following 6 categories: third-party dataset, which means whether that URL is linking to a dataset and is provided by a third party. The second category is third-party software, which means that the URL is linking to a software and it's provided by third party. Author-provided dataset is the type of URL that links to a dataset, but created or maintained by the author of that particular scholarly publication. Author-provided software is the type of URL that is linking to a software and created or maintained by the author of the scholarly publication. So sometimes there are URLs that links to both dataset and software. And for such resources, we have created the category called project, which means this kind of URL links to both dataset and software. And the last category is general URL, which is basically the URL that doesn't link to either dataset or software. So for the labeling, we have these samples were manually labeled by 2 graduate students who achieved a consensus agreement rate of 92%. And when there were disagreements, that was resolved by a third annotator who has expertise in this arena. So these are a couple of examples for each category of our dataset. So the third-party dataset is about 20.5% of our OADS 1K dataset. And from the example, we can see I have used some XML tags called pre, target, and trail. So the pre tag means is used to identify that sentence is a preceding sentence. The target tag means that particular sentence is a target sentence containing the URL, and the trail tag refers to the trailing sentence. So from the first sample, we can see that it's talking about a dataset that was downloaded from this particular website, and so that's why we have annotated it as third-party dataset. The second example refers to a software called Veni, which was used to create the Venn diagrams, and it's so we labeled it as third-party software, and the third-party software is about 19.6% of our dataset. The third example is an author-provided dataset example. We can see that from the target sentence, it's talking about a dataset that was created by the authors itself and was made publicly available on this through this link. So we have annotated it as author-provided dataset URL. So the fourth example is the author-provided software example. This is interesting because when we look at the target sentence, we can see that it clearly mentions about code. The URL is linking to a code repository. But however, just looking at the target sentence, we cannot surely say whether it's author-provided or third-party. So for that, we had to look this sentence preceding that target sentence, which clearly says that we implemented the Monte Carlo-based VS method described in sections 2 and 3 using that. So it means that this particular code was implemented by the authors itself. So we annotated it as author-provided software. Okay, so we can see that the project URLs were about 8.4%, which is the lowest number of samples in our data set, and creates a little bit of class imbalance. And we can see that that particular GitHub link is referring to a repository which includes both code, data, and documentation. And the final category is general URL, which links to something other than dataset and software. So let's talk about the Ensemble ODS classifier architecture we have developed. So as I mentioned earlier, that the Ensemble ODS classifier basically is based on the Ensemble learning, and it combines three models, which are a supervised contrastive learning model, a cyber-based model, and a BERT GCN model. We use these three models to individually get a prediction of a particular sample. Then we use those prediction, and based on majority voting, we decide the final prediction. So whether a majority agreement was reached, if at least two models agree, then we reach to the final prediction. And if not, where there can be cases where none of the models agree. So that's when we take the prediction from BERT GCN, because from our analysis, which I'm going to show later on the presentation, that BERT GCN has outperformed individually the cyber-based model and the supervised contrastive learning model. So let's talk briefly about the supervised contrastive learning model. This model is particularly useful when there is the data scarcity, and it improves contextual representation by grouping semantically similar samples. In this particular work by Gunnell et al., who proposed this model, combines the cross-entropy loss and the supervised contrastive loss, which were introduced by the authors. And the cross-entropy loss was basically used for penalizing the incorrect predictions, and the supervised contrastive loss was introduced to encourage representations of same class samples to be closer and different class samples to be apart in the embedding space. So for this work, we have used the input, which is the concatenation of the preceding sentence, the target sentence containing the URL, and the trailing sentence. And for generating the embedding, we have first used a tokenizer, Spectre-based tokenizer, and the Spectre-based encoder for generating embeddings. And any BERT family model could be used, let's say BERT, Cybert, or DistilBERT. Yeah, so we have experimented with BERT, DistilBERT, and Spectre tokenizer and model, and we have decided to go with the tokenization and encoding of Spectre because it outperformed the other two. So for the second model, cyber-based model, we have decided to choose it because Cybert was pre-trained on a large corpus of scientific publications from Semantic Scholar, and it captures domain-specific context and terminology better than general-purpose models such as BERT. And it has also proven effective for scientific NLP tasks, including URL citation classification that I have earlier talked about when I was discussing the related work. So for this model also, we have used the same input set: preceding sentence, the target sentence containing the URL, and the trailing sentence. And the tokenizer was used based on Cybert's case version model. And for fine-tuning the model, we have used the same Cybert-based case version for sequence classification. The third model that was used was BERT GCN model, which basically integrates the pre-trained language model with the graph-based transductive learning. So for this, we had to pre-process the data to create document nodes and word nodes for generating the graph. The document node is basically the embeddings of the preceding sentence plus the target sentence containing the URL and the trailing sentence. The word node represents the embeddings of the words across the dataset, and the word to after input and pre-processing and the graph construction, where the word-to-word edges were weighted by positive pointwise mutual information, and the document word edges were weighted by TF-IDF. So then simultaneously we fine-tuned the BERT and trained both BERT and GCN jointly using the cross-entropy loss on labeled nodes to propagate those information. So the purpose of using PPMI was to find out the co-occurrence of words in a particular sample, also throughout the dataset. And the document word edges were weighted by TF-IDF to know which words were frequently co-occurring, were occurring in the whole dataset, as well as the particular concatenated sample. So to evaluate the performance of OADS URL classification models, we have used our OADS 1K benchmark dataset, and we have done a stratified split where 80% of the data was used for training and 20% to test the model. And we had proportional representation across classes. So the models that were evaluated, we have done a couple of experiments. Let's say for the supervised contrastive learning model, which is also part of the Ensemble OADS classifier, we have experimented with different language models such as BERT, DistilBERT, and Spectre. For Ensemble OADS classifier, we have performed experiments with different input combinations, which I'm going to talk about later. And then we have showed a comparison between the baselines, which are LLM-based few-shot classification done by GPT-4, the Claude 3.7 Sonnet, and Cybert, BART GCN, and our previously developed OADS classifier. So let's see how the supervised contrastive learning performance with different language models. So from the table, we can see that when we used Spectre, it as tokenizer and for encoding, it outperformed other two language models, BERT and DistilBERT. So for our final model, when we use this as part of our Ensemble OADS classifier, we use Spectre for tokenization and encoding. This is where we have done experimentation with Ensemble OADS classifier for two different input combinations. The first input combination is just the target sentence containing the URL. The input 2 is the concatenation of the preceding sentence, the target sentence containing the URL, and the trailing sentence. So from the table, we can see that the F1 score achieved through input when we trained the Ensemble OADS classifier on input 2 outperformed when it was trained on input 1. And the best F1 score macro average was 0.9, which is 90%. So we have also done some experimentation with LLMs. So we have developed two LLM-based few-shot classifiers with models GPT-4 and Claude 3.7 Sonnet. So we have developed this was based on few-shot prompt engineering, where we have created the prompt template that includes the task description, which is our OADS URL classification, the definition of 6 URL categories, and then we have included 10 annotated samples covering all classes in the prompt. Then we have told the model to strictly output the category name. So for reducing LLM stochasticity, we have set the temperature to 0, and we have run the prompt for each input 5 times. Then we have applied the majority voting strategy. So basically, we collected 5 predictions per input, and the final label was decided, where the most frequently predicted category was king. So this is just the overview of the hyperparameters we use for Ensemble OADS classifier. So one of the class models in Ensemble OADS classifier is SEL.
Yeah, we need to focus on wrapping this up, please.
Okay, sorry. So I will just skip the slide, and these are the evaluation results where we are showing the comparison between all the baselines and our model. So we can clearly see that Ensemble OADS classifier outperformed all the individual models that is the part of the Ensemble OADS classifier. It's because each model that we have used in this Ensemble OADS classifier is basically diversified model, which basically strengthens the performance of the Ensemble classifier. And so the best F1 score we have achieved is 90% for this classifier. And so basically we have proposed this Ensemble OADS classifier that combines Cybert, SEL, and BERT GCN to classify scholarly URLs in 6 categories using their context and expanded context, and it outperforms all the baseline classifiers and achieved F1 score of 90%. So the limitation of our work is that our dataset is small and it exhibits class imbalance, especially in the project category. So our future work is includes expanding the dataset and address the class imbalance, augment the dataset with samples from diverse academic disciplines to enhance classifiers applicability and leverage LLMs to generate artificial URL contexts and expanded training contexts. So that's all about my presentation. Thank you, everyone.
All right. Thank you. Questions, comments for Lamia? Anyone? So Lamia, did you investigate simple rule-based classifiers as a baseline, like looking for things like, if it's github.com, it's, user contributed software, or even .edu, or looking for file extensions like .zip, .tar, .csv, something like that?
So no, not just exactly a rule-based as baseline, but we have retrained our previously hybrid model ODS classifier that is based on rule-based and binary classification.
All right, so that's rolled up in the third from the left column there.
Yes, you're right.
ADS classifier. Okay, got it. All right. Any other questions, comments? All right. Thank you. Next up would be Akshay.
Hey, hi. Yeah, you go ahead and share my screen.
All right.
Can you guys see that?
Yep, got it. Thank you.
Perfect. Just a second. Hey everyone. Good afternoon. This is Akshay Nayak, and today I'll be presenting my paper adapting online customer reviews for blind users, a case study of restaurant reviews. Basically, we propose QuickQ, a web Chrome extension that helps improve the accessibility of online customer reviews for blind users, specifically focusing on restaurant reviews. The motivation stems from the fact that there is a growing importance of user reviews in consumer decision making. And we conducted a very detailed user study for the development of QuickQ. Through this, we aim to bridge the accessibility gap and make review content more meaningful and usable for blind screen reader users. Online reviews have become a cornerstone of consumer decision making, whether it's choosing a restaurant, booking a hotel, or buying a product online. People rely heavily on peer-generated content to guide their choices. These reviews are perceived as more authentic and trustworthy compared to traditional advertising. In fact, reviews are so influential that even a small shift in ratings can significantly impact a business bottom line. For restaurants, in particular, customer reviews highlight specific aspects like food quality, service, and ambience, all of which directly affect potential customers' perceptions and decisions. This widespread reliance on reviews underscores the importance of ensuring that everyone can access and benefit from them, including blind users. While online reviews are widely used, interacting with them isn't always straightforward, especially when there are hundreds of them, and even thousands. Users often face several challenges. First, the sheer volume of reviews makes it hard to go through all of them. Second, there's a lot of repetition. Many reviews say the same things using different words. Third, some reviews are simply irrelevant or outdated, adding noise rather than value. To help manage these, platforms have introduced solutions like AI-generated summaries, keyword-based search, and sort by usefulness options. However, as we'll see shortly, these tools are mostly designed for sight users and don't effectively support blind screen reader users who depend on screen readers. Despite the advancements in review platform, the majority of their features are optimized for sighted users. Sighted individuals can quickly skim and scroll and prioritize content visually. They use layout cues, bolded keywords, star icons, and more to identify information more quickly. But for blind screen reader users, this experience is completely different. They rely on screen readers, tools that convert on-screen content into linear audio. This means information is consumed sequentially, often with the keyboard shortcuts. This causes what we call listening fatigue, especially when reviews are too long, repetitive, or poorly structured. Even in terms of AI-generated summaries, they fall short. They tend to be too generic, covering many aspects at once, failing to address specific needs like, say, what about good food, or what's wrong with the service, where users have a specific question in their mind. This usability gap is exactly what our work aims to address in this solution. Here's a demo of how traditional screen reader usage looks like. Okay, that basically illustrated how the one-dimensional sequential nature of screen reader navigation. To better understand the real challenges faced by screen reader users, we conducted an in-depth interview study involving 30 participants. These participants represented a diverse group in terms of age, gender, and professional background, including students, teachers, and social workers, and freelancers. All of them were proficient screen reader users. Most users used JAWS screen reader, while a few did prefer NVDA. We recruited them through email lists and word of mouth. To explore the challenges in depth, we conducted a detailed semi-structured interview study. This format allowed us to guide conversations while giving participants the freedom to elaborate on their personal experiences. We started with carefully crafted seed questions such as, what challenges do you face when browsing for reviews? What kind of information do you typically look for? What would make the experience better for you? Interviews were conducted remotely, either via Zoom or phone, and lasted around 45 to 60 minutes on average. We transcribed these interviews. We then used qualitative analysis techniques that included open coding and axial coding methods to analyze this transcribed information. This helped us identify recurring themes and patterns across participants. These insights were foundational to the design of our solution, ensuring that the solution was grounded in real user experiences and needs. The findings of our study. Our study revealed several critical usability issues faced by blind screen reader users when interacting with online restaurant reviews. These issues included, first, there was a widespread complaint of information overload and listening fatigue. Many participants shared that they often stopped after just 3 to 5 reviews because the content was too repetitive or uninformative. For example, one participant even said, I just give up. It's not worth going through the same things over and over again. Second, the users encountered outdated reviews. For instance, participants mentioned reading about dishes that were no longer available or comments that no longer reflected the restaurant's current services. Third, there was a strong desire for structured information. Nearly all participants wanted the reviews grouped by aspects like food, service, ambience, pricing, and hygiene. They also wanted to see positive and negative summaries for each. This structure would allow them to focus only on the parts of a review that matter to them, making the experience much more manageable. These findings is what informed the development of the assistive tool, that is the Quick Queue. Now, coming to the Quick Queue's browser extension, giving a brief overview on the user interface. A Quick Queue was developed as a browser extension on the Chromium, on any browser that supported the Chromium. So Quick Queue integrates directly into Google Maps and augments the existing user interface without requiring using to switch pages or applications. The UI is designed as a hierarchical accordion-style structure with 3 levels. The top level shows the 5 main aspects that users generally care about. That is the food, service, pricing, ambience, and hygiene. At the second level, under each aspect, Quick presented positive and negative summaries generated by a large language model. And the third included the raw original reviews grouped according to the aspect sentiment pairs. This layout drastically reduced the information overload by helping users focus only on what was relevant to them. It's also fully compatible with screen readers. The UI was fine-tuned with ARIA landmarks, attributes, and for accessibility, and it was navigable by simple keyboard shortcuts like Tab, Shift Tab, Enter, arrow keys, or Escape. This made it easier for even the most novice screen reader users to use the tool without much proficiency needed. The goal was to let users listen but understand more, giving them a faster, structured access to exactly the information what they wanted. Coming to the overflow schematic of QuickView, at a high level, the process begins at extracting reviews directly from the Google Maps interface using predefined XPath rules. Once the data was captured, there were two key stages to it. One is the joint classification and then the focus summarization. In the joint classification step, we captured all relevant reviews and classified them to an aspect sentiment pairs for each review. For example, the review that said great food, but slow food service would be labeled as positive for food and negative for the service. Then we had the focus summarization. After the classification, the reviews within each aspect sentiment category were summarized to avoid redundancy and reduce any kind of listening fatigue. The output was passed to the front end where it's structured into a layered accordion style, like I showed you guys before, and which was accessible. All the components communicated via JSON, to a structured JSON, which made it easier for the UI to present it. We used GPT-4 and LangChain, which is basically a Python framework that helps you write AI-based coding and communication with large language models. This entire pipeline runs through a Chrome extension. There's no require for additional user input and beyond standard navigations. Now, going in detail about the first step, the joint classification process. We extract, like I mentioned, we extract all applicable aspect sentiment pairs for each of the reviews. This is crucial because a single review can touch on multiple topics with both positive and negative sentiments. Like I mentioned, say something like the food was amazing, but the service was terrible. The food can be classified under positive sentiment and the service on the negative. To achieve this joint classification, we use the GPT-4 model, which was guided through a prompting technique known as CARP, the clue and reason prompting technique. What this prompt did is it instructed the model to first identify cues, keywords, phrases that point to specific aspects or sentiments, and then perform a set of reasoning to justify what clue maps to a particular classification. Finally, we had an output. The LLM provided an output, a complete list of aspect sentiment pairs for each review. This was done iteratively for multiple reviews. This approach is more effective than a simple keyword matching because it can handle certain nuanced language that LLMs are capable of. It's especially useful in reviews that mention sometimes very contradicting opinions, like praising the food, and criticizing some other aspects of the same restaurant. Now, we did evaluate this joint classification. We created a ground truth data set of 50 manually annotated restaurant reviews. These were sampled from a diverse cuisines and geographic locations. Each review was labeled with all applicable aspect sentiment pairs, a total of 10 possible combinations across 5 aspects and 2 sentiment polarities. We tested 2 prompting strategies initially, although we did use a few shot CARP at the end for the testing of the system. The zero-shot CARP prompting and few shot prompting techniques with 20 examples. The difference was quite clear. The few shot prompting technique achieved a precision of 0.8 and recall of 0.82 and an overall F1 score of 0.81. The zero-shot prompting initial scored quite low, 0.62 across all metrics. This was confirmed in the paper as well, where CARP was proposed, where the few shot prompting techniques with the CARP technique proved to be superior than the zero-shot technique. So it was clear that we had to include a few examples of prompt to improve the classification accuracy, especially when reviews were quite complex, where they mention a lot of aspects with different sentiments for each. Now, coming to the focus summarization, after classification, the next challenge is summarizing the reviews, but not just any summary. We needed focus summaries that highlight only the information relevant to that particular aspect sentiment pair. For example, if a user selects service and negative, the summary should only include complaints about the service, not any random food comments or unrelated praise. To achieve this, we did use another prompting technique called directional stimulus prompting. With GPT-4, the DSP works by feeding the model 2 key inputs, the target aspect that is in some cases the example service, and the desired sentiment, that is the negative. These act as a directional signals telling the model to filter out any unrelated content and focus only on what matters for that aspect and tone. The generated output was very concise, bullet point list and summary of making it easier. That made it easier for screen reader users to quickly grasp what's good and not so good about a particular aspect of a restaurant. This step was included to avoid the listening fatigue by prioritizing clarity, relevance, and avoiding any noise in the summaries that was generated. We did evaluate the performance of the summary as well. So to do so, we built a test data set of 50 samples, 5 for each 10 aspect sentiment pairs. Each pair we manually crafted the ground truth summary and asked 10 human annotators to evaluate the GPT-4 responses. They scored each summary based on 2 key metrics on a scale of 1 to 10, factuality and noisiness. The factuality basically determines whether a summary accurately reflects the original reviews, and noisiness, does it avoid off-topic or any irrelevant content. The results were quite promising. Average factuality score were around 7.9, and for noisiness, we received a score of 8.3. This scores indicated that the summarization method was quite accurate and focused, proving to be quite reliable. However, there were a few imperfections, as the numbers tell us, which typically stem from the conflicting sentiments in the source data or subjective wording, issues that we expected to improve further with prompt tuning and model updates. Still, these results were quite effective for usage in QuickQ. Now, overall system evaluations, we did conduct an overall QuickQ evaluation in a real-world scenario. We conducted a user study with 10 blind participants. All participants were proficient screen reader users. Once again, most of them specifically preferred JAWS and had prior experience navigating online reviews. Importantly, none of them had taken part in the study in the earlier interview study. We used a within subject design where each participants compared restaurants under 2 conditions: the default Google Maps interface with just a screen reader and the QuickQ augmented interface. The task was to evaluate the restaurant reviews and make a dining decision, simulating a real world case scenario. To minimize learning bias, we used different restaurants for each condition and counterbalance the order of tasks using a Latin square method. Each session lasted up to 30 minutes, and participants were observed as they navigate the interface with feedback collected via questionnaire and interviews later on. This evaluation setup allowed us to directly measure both usability and improvements of the system compared to traditional browsing. Coming to the results were demonstrated as demonstrates the usability of the system. We did use a system usability scale, the SUS. The default screen reader interface scored an average of 63.25, which was considered marginal. In contrast, QuickQ had a very superior performance in terms of usability, where it scored 81.5 on SUS, quite placing it on the excellent range. This difference was quite statistically significant, showing that participants found QuickQs much more usable than the traditional browsing of restaurant reviews. Now, looking to the task workload, now the NASA task load index, the NASA TLX index that was used, the screen reader condition had an average score of 62.1, while QuickQ, the workload dropped significantly up to 38.4. Once again, this was statistically significant. This indicated drastic differences in the cognitive load perceived by the participants regarding QuickQ and traditional browsing. So the quantitative results were very clear. The QuickQ outperformed the traditional screen readers in terms of usability and cognitive load. No, we did analyze the qualitative feedback using similar qualitative analysis techniques or coding techniques. So the users appreciated the simplistic design and how it relied on familiar keyboard shortcuts. So this meant they didn't have to learn any extra keyboard shortcuts for the system. Like I said, simple keyboard shortcuts such as tab, enter, arrow keys, and escape was sufficient to operate the system. For example, one participant said, if I had these summaries, I won't even listen to the full reviews. Full reviews were quite frustrating and irrelevant, so this made it easier. Second, the participants loved the aspect-based summaries, which allowed them to explore new items and restaurant reviews that they might have otherwise skipped. All participants asked if the QQ could work on other platforms, including Amazon. This showed that there was a strong demand for this kind of accessible information on user-generated content, which we do address as part of our future work. Final users pointed out that comparing multiple restaurants was much easier in terms of in QQ, which would be quite difficult in the default user interface. Now coming to the discussion, first we list out the limitations. Our evaluations was limitation to JAWS screen reader users on Google Chrome and Maps. Although JAWS was widely used, it is necessary that we test the usability of the system to NVDA and voice over users in order to ensure that the system is quite generalizable. Second, QuickQ currently supports only English language restaurant reviews. It is essential that we expand this platform to other languages. LLMs have proved extremely capable in translating, so this should be easily integratable in the future work. Third, our data sets for training and evaluations were quite small due to the intensive manual effort that was involved. Larger data sets must be included to help us better validate the system of joint classification and summarization modules. Lastly, participants also requested mobile support since many users mentioned that they usually browse reviews on their phones. This browser extension was limited to desktop-based navigation, but we hope to explore browser extension. Browser extensions cannot be easily built on mobile phones. That's something to be noted due to its own privacy concerns. So in the future, we hope to somehow integrate mobile phone support for similar navigation in Google Maps in phones or any other customer reviews on any other platforms. Yeah, in conclusion, we built QuickQ, a Chrome extension that would enable blind screen reader users to navigate user reviews much more quickly. This paper was lauded for its accessibility and the Web for All conference. In fact, it was awarded the best paper for this year, around a week ago. So the reviewers were happy about how we explored the LLM-powered joint classification and focus summarization methods and how it improved the overall usability of accessing restaurant reviews for blind users. Thank you.
All right, excellent. Thank you. Questions, comments for Akshay?
May I ask you a question about the evaluation? I don't know the slides number, I'm sorry, but at one point you're talking about you were using, so can you go back? Yes, so for the matrix, no, next slide.
Okay.
Yeah, the factoriality score from 1 to 10, a noisiness score. But I don't see that in the, so for this, how do you calibrate the scoring? I mean, when do you calculate the scores automatically or you use human?
No, this was a human evaluation. So this is a Likert scale based on evaluation.
So if you use human, then how do you calibrate this? Let's say for different people, they have different standards for 1 and 10.
Yeah, indeed. So we had multiple annotators rating the summaries that was generated by the large language model. Which we address as a limitation, like I said, it is subjective scoring. So in the future, we hope to bring some kind of an automated metric. So basically, there were research that indicated that automated metrics or automatic evaluations have its own limitations, that they are not reliable. There was research that stated that, and prior research, including in our own work, in prior work in EHCS, in InstaFetch, we did manual evaluations. We did try using Blue and Rogue, but the reviewers did prefer some kind of a manual evaluation, which evaluated the summaries overall for against the ground truth.
Okay, thank you.
Yeah.
Got a couple questions if you got a couple minutes.
Yeah, I do. Please go ahead.
Please put page numbers on your slides.
Yeah, I will include that.
That's good because I've got a couple slides that I can't tell you how to get to because there's no page numbers. Take that as a broad hint. Okay, off my soapbox. Getting back to the page that you just had where it has a noisiness, that one.
Yeah.
So Let's go with one. Oh, God, hurts. Okay, this one, the noisiness score measures the absence of irrelevant information. How can you measure an absence?
So noisiness score basically indicated that there was no irrelevant information. So basically, if I'm talking about service and positive, we needed to make sure that the summary did not talk about, say, food or say any other sentiment that was not relevant to that particular aspect sentiment summary. So it was
a more relevant way to
no,
measure that
this
would
was
be,
kind of like a negative thing of so
how
one
about measuring the
indicator.
presence of irrelevant information?
Oh, that would revert in the whole scale, right? If I use presence.
Yeah.
So
Okay.
yeah.
I think it is the page before that, I think. Somewhere you've got a page, the title is evaluation. Okay. Oh,
Yeah.
but all
Yeah.
right. Go back to your box score thingy.
Okay.
That one. On the left-hand side, having a high score is good. On the right-hand side, having a low score is good.
Yep.
Why? Why can't having a high score be good all the time?
Because these Likert scale questions that we use for so usability analysis in HCI. In SUS, a higher score is good because on the Likert scale, a higher scoring basically indicates the system is more usable. Whereas on the right side, we measure the cognitive load. A higher number indicates a higher cognitive load, so less usable. The system is less usable.
No. Okay. One last thing, and you've got, I think it's on the slide titled Joint Classification Performance, I think.
Yeah.
Yep, that one. When you were reading this, you did it the way a human being does it. In general, nobody cares about the third digit after the decimal point.
Oh, okay.
And when you were reading it, the numbers that you were reading that I heard were 0.8, 0.82. So you were verbalizing that the things after the third decimal point really don't make a lot of difference.
Okay.
I think the project is interesting. Yeah, if you can figure out a way to get it into the hands of more people, like a mobile app of some sort, it has real potential. I think it's kind of neat. Good luck.
Yeah, thank you. Thank you so much. I appreciate it.
I'll just do one quick question before we jump to the last one. So I was sitting here trying to figure out how this could be extended, and you address that in your later slides, beyond Google Maps as a platform, beyond beyond restaurant reviews as a domain. Then it occurred to me that perhaps one of the things that distinguishes restaurant reviews, perhaps even more than just like product reviews, is this issue of time. And did you account for time in your summarization at all? Because for long-lived restaurants, the fact that the food was good or the service was good 5 years ago might not, and mean that it still is today. And now, and maybe the Google Maps platform already sort of rank orders by time. But anyway, I was wondering if your analysis had any concept of time in it.
For now, we didn't define a particular time, but the idea was generally to include the reviews for the last 3 to 6 months because that would be the most relevant.
Right.
Because that would make sense because older restaurants undergo drastic changes over time. And like you said, most of the reviews wouldn't hold good for today. So the idea is to only include most relevant recent reviews.
Right. Okay. Yeah. And and possibly for products, maybe that doesn't change over time, right? If I'm buying shoes or something like that, I assume they're kind of the same.
Yeah, I think there it would be a little bit subjective because there are a few products that also do undergo a change.
Right.
Yeah.
All right. Well, that's all that I had. Thanks so much. And then our next and our final presentation is going to be John.
Yeah, can you hear me?
Yep.
All right.
Okay, got it.
All right. All right, can you see my full screen?
Yep. Thank you.
All right, good afternoon, everybody. My name is Jhon Botello. I'm a PhD student in computer science. I joined in fall 2023. Since then, I've been working under the supervision of Dr. Michel Weiger. I'm also a GRA at VIMAS, working with Dr. Jose Padilla and Dr. Erika Friedenloh. So today I'm happy to share this research topic I've been working on. The title for this presentation is Exploring Large Language Model for Analyzing Changes in Web Archive Content, a Retrieval-Augmented Generation Approach. This specific work was presented in the 9th Computational Archival Science workshop in 2024. This workshop was part of a larger IEEE Big Data conference in December 2024. Unfortunately, I wasn't able to attend to that conference. However, my coworker, co-authoring this paper, Leslie Frew, she was able to attend to the conference, and she did an amazing job presenting this work. So today I'm gonna walk you through this presentation. It's represent our early exploration at the intersection of AI and web archiving. Specifically, I'm going to talk about how large language model can be leveraged to analyze how web archive contents change over time. So yeah, let's get started. As we can see here in this slide, people are interested on tracking how web pages change over time, and this is just one example of that interest. During the period of 2016 and 2020, there is evidence that under the Donald Trump administration, some climate change related terms were deleted from federal websites, and the headlines are like evidence of that. So it tells us that people, it could be like a researcher, a journalist, or the public in general, are interested in tracking this kind of changes. It tell us something. Well, it does not affect only like the public access information, but also it might raise concerns about, it could be transparency or the long-term integrity of the web content. So now the question is how we track this type of changes. So as many of us know, a web archive preserve historical version of the web pages. They capture how they appear at a specific time. So what you are seeing here is an example from climate.gov. This web page was archived in March 4, 2016. So the calendar interface let us explore different capture dates. And by clicking on a specific timestamp, we can view exactly how the page appeared at that specific moment. So this is just an example. And it's important to recall that there are multiple archives, and the Internet Archive Wayback Machine is the most well-known example because it has captured over 916 billion web pages to date. So just to keep that in mind. So to bridge the gap between the live web and the archive web, we have the Memento protocol. So it connects an original URI. We call it the original resort, and URIR, with the Memento. We call it the URIMs, which stand for Memento. So it's like the archive version of that specific web page. So we can go back on time. So with this, or by following the Memento framework, we have a way of systematically retrieve and compare different versions of the same web page over time. And this is essential for understanding how web content evolve over time. So now we can think about how to store this. So to store web archive files, we use a standardized format, which is called WAR file, which stands for Web Archive File Format. So each WAR file may contain one or more WAR records, and each WAR record stores one snapshot of the web content. So the snapshot may include like a complete HTTP response headers, the HTML content and any additional resources, like it could be images and JavaScript file. So here at the right, we can see the internal structure of a WAR file. So we can see here a WAR record. It has like the text header and the content block, and the text header has like a kind of a metadata that we can see here, and it contains like the content length, the WAR record, and the WAR date, and yeah, stuff like that. So now we can think, now that we know this, we can think about, like, okay, how we track this type of changes. So we can use that, the Internet Archive Wayback Machine. However, finding website changes is often a manual process requiring significant time and effort. So what you are looking at here is the capture calendar for this web page, climate.gov Ensemble. This site has over 15,000 captures between 2016 and 2024. So to detect changes, a user would typically need to click through individual captures, as you can see here, and then compare them visually and analyze any difference. But we can see like, okay, but there are tools. For instance, this here it says changes, and we can think there are some tools, and indeed that's the case. For instance, the Wayback Machine Changes tool allow users to view terms-based difference between web pages. It highlights in yellow some content, the content that was deleted, and it highlights in blue the content that was added. There is another tool, it's called like TMVs. It allows users to view visual differences between web pages over time as well. However, this was focused, it allows us to see structural changes visually. So even though we have this type of tools, they fall short when it comes to analyzing or to capture complex semantic level changes. If we see here, we can see what changed. However, it could be kind of hard to analyze like the semantic change here because they are kind of piled. So we can see that, however, it can tell us what changed. However, it doesn't tell us about the meaning. What is the semantic context behind that change? What would be the intention of the change at some point? So this is just an example. This is a capture of the climate.gov in 2016, and this is a snapshot from 2020. So we can see here that while the overall layout of the web page remains kind of similar, there are some changes in the content here. For instance, it's like we can like focus on this one. So on the left, the advisory indicates that El Niño continued like during December 2015, and it highlights like its global impact, and also it forecasts like that the event will persist for some time. And here on the right, the content, we can see that it has shifted to a status update, as we can see here, and it states that ENSO, which stands for El Niño Southern Oscillation, now is not active. So and the forecast is like this is a suggestion that there is a 60% chance of like neutral conditions. Now these are not just like textual changes. They reflect also like a semantic change in the state of the system here being reported. So now it's not about just what change, it's about what is the meaning of this change, what is the semantic change in this website. And also we can think about other type of changes. For instance, this one, like what is El Niño, and then is what is ENSO. There is a change, and maybe the tools I was talking about, they highlight what changed. However, El Niño and ENSO means completely the same in this case. So we need something to try to track those type of like semantic changes. So what do we need? We need a way to detect semantic changes in web content. And what do we know? We know that LLMs are very strong at understanding language and meaning. So we also know that we can enhance LLMs performance, and we can set LLMs for a specific task by providing additional content or additional knowledge. And there are a couple of methods for this. One of the most well-known would be like fine-tuning, but we also have Retrieval-Augmented generation, which is the one we focus on in this work. So this is a tool that this tool was released last year in February 2024 by the Harvard Library Innovation Lab. So this is WarGPT, and WarGPT is a RAG approach. It's a tool that enables creating custom chatbots that use web archive collection of a knowledge base. Now the question is, can we use like a RAG approach to analyze changes in web content? So that was like what motivated our work in this case. So this is the architecture of WarGPT. So we modified it to look for semantic changes. This overall, this is like a general RAG architecture, but the difference in WarGPT is that they use a collection of WAR files as a knowledge base. For our specific case, we are focusing on if we are able to analyze like changes among like mementos. So our knowledge base was WAR files, but like it was mementos in general. Then it goes to an ingestion pipeline where from the WAR file we extract or WarGPT extract the text from the records. It extracts from the header. It extracts like the metadata, which is like the date, and it extract the date when the web page would archive. Extract also the URL, all the URIs in that header, and then also extract from the HTML it extract from the HTML the text the text in general. So what we did as well was export the text to a plain text file for using in evaluation, comparing the answer from the LLM with the plain text with the original content in the web page. Then it goes to the we split it into chunks. It goes to embedding model with storing into a vector database, and then we designed 2 queries to evaluate that. I'm gonna show you that in the next slide. But then the query goes here. We use like Gaussian similarity to extract what like the changes, and then we get the results. We get the chunks that were retrieved, and it goes to the query, and we got the context prompt, which is important for like this specific task. It's like control the way the LLM is gonna answer. And then it goes into the LLM, so the LLM is gonna be able to compare the two, like the two versions of the web page, and it's gonna provide an output for us. So our specific use case was using mementos from US federal environmental web pages that we knew that they changed between 2016 and 2020. And these web pages, these WAR files were obtained from this work from my colleague and co-author in this paper, Leslie Frew. So we select like a random sample from here, and then after that process, we got 10 web pages from NOAA, 8 web pages from NASA, 3 web pages from the US Department of Energy, and 9 web pages from the United States Environmental Protection Agency. So that was what we compared. So we had 2 mementos for most of the web pages, like a memento from 2016 and a memento from 2020, but we also include like more than 2 mementos to see if the RAG was able to compare more than pair of mementos. So we designed 2 queries. We empirically designed them. The query number 1 was like, what are the changes or inconsistencies in internal phrases or paragraphs among the mementos of web page X? And in web page 8, we were passing the URI, the original resource. And then the second query was like compare any change regarding the semantic context among the momentum for the web page X. So every answer from the LLM were validated through human evaluation. So we were checking each answer and then comparing the answer and checking the plain text file where we had the original content and checking if it was accurate or not. We were like doing it like in a binary classification, like is it accurate or not, 0 or 1, if it was like okay or not. If the LLM, what the LLM was saying was true or wasn't true. The answers are here in the GitHub, so you can check it out as well. So with the query number 1, we were trying to check like what kind of changes we can extract from this approach. And here like focusing directly in the semantic context and the semantic changes overall. So this is the results we got. And this is like an example of one of the web pages we analyzed from the Environmental Protection Agency. So we can see here, this is the memento in 2016 and this is the memento in 2020. And there are a couple of differences here. The layout looks like kind of similar, but we are not focused on the layout, we're focused on the content. I call it like content in the body and structure, content in the structure, meaning that something changed in the header or in the footer. So here we can see that in the general in the body, before there were like some webinar happening at this specific moment, and then those webinars like changed, so there is like a shift in the content. Now we are having like a broader content for the webinars, and this is the answer from the LLM. This was for query number 1. So we can see that in the 2016 version, the web page mentions a series of webinars, including introduction to eChow and intro to acts in eChow. So it mentioned like the events, the date, and by 2020, the content has expanded to include more detailed description of various webinars, and it like mention what the webinars are. And here is the second one. The semantic content of the web page has evolved over time, reflecting changes. And the changes are like expansion of webinar topics. Initially, the focus was on introducing each website, which we can see that here because it was like an introduction. The website and its basic functionality. This is what we can see here. But by 2020, the webinar has expanded to include more advanced topics and detailed demonstrations. So we can see that we are getting that. So overall, the result for most of the pages were okay. As I said, we were analyzing like if we were finding that type of changes like in the content in the body, and any change in the structure, meaning any change in the content in the header or in the footer. This is what it's been analyzing that. So most of the results were okay. This one was not okay. In this one, it was not accurate, meaning that the mementos or the chunks that were extracted, that the LLMs, the retrieval part say that where they underscore changes, those changes were for another web page, and it's because the web page had the same domain. It was kind of like climate.gov ENSO, and it had the same domain. So because of that, it was extracting that. However, we had a bunch of web pages with the same domain, and it only happened in only one. It only happened one time. So yeah, the exploratory study will have like some limitation. First is like we use only 30 web pages. In total 77 WAR files, because it was one memento from 2016 and one from 2020, but sometimes we had more than 2 mementos. And then when pages belong to the same domain, the system might extract incorrect passages. We saw that only one time. However, it would be great to like escalate this and see if the same pattern is applying for a larger study. And the other one is that we still rely on WAR files. So we have been applying we have been thinking about how to move forward because like downloading the WAR file itself, it takes a long time, it's time consuming. So we can think about having a specific URL, then how can we analyze changes in our web page only using the URL? So this is kind of like a modified architecture for that. Having a URL, we extract the CDX data. From the CDX data, we're gonna have all the mementos, the URIMs, and then we do the crawling process, and then we store it in a wet format file, which is for WAR encapsulated text. This type of files only contain like the body text of the web pages. It doesn't include HTML, images, or any other type of resource, because in this case, what we care about is only about the text. So then it goes to the ingestion pipeline, we get the routers, and then we generate embeddings, and then we are able to ask questions. This is how this is what that framework look like. So we build our own RAG pipeline. This is like moving ahead to that paper I was presenting, like some stuff we have been working on recently. So we have here, this is an example of USD. We have the web page, the URIR, the original resource. We put it there, and then we get the CDX data, and we are able to see or like all the mementos, all the capture from the CDX data. So we visualize them, and then we are able to select a specific range we want to analyze here. So let's suppose I select from 2016 to 2017. So then I'm able to ask questions about all the snapshots or the capture, the mementos that were there from 2016 to 2017. So this is, then we can play with it, and then we can ask for any, like, give me a timeline of changes. So this is what we are getting here. Over time, it highlight the changes. For instance, we can see here from in February 4 in 2016, this changed, but in February 5, it says no significant changes, continue emphasis on Ensemble impact. So at the end, we're getting like a timeline, and we can see like how the web page evolved over time from a semantic level. So our future work include like exploring the integration of multimodal models to analyze text, to analyze not only text, but also images. It will be used in a WAR file, but it could be like from a crowding process as well. We would like also like investigate the use of any other type of LLM, such as Climate GPT and LLM 360. These are open source, so also we can evaluate the differences in the responses about changes from different like kind of perspectives from different LLMs. So in summary, these are the conclusions. We explore the use of GPT-4o. By the way, we use in this case for our work, we use GPT-4o. However, in this rack, we propose like integrating other type of LLMs. As you can see, we have Phi, Llama, or Mistral. So we demonstrate that LLMs provide deeper analysis, but capturing semantic context. Unlike traditional methods focused on term frequency or surface level differences. And also we established like a foundation for future research in web page change analysis, advancing the integration of web archiving and artificial intelligence. So that's all.
All right, thank you. Questions, comments for Jhon?
Hi, I have a few questions. First of all, so in your research, you focus on semantic changes, is that right?
Yeah, the semantic changes.
How do you define a semantic change?
Well, in this case, let me go back here. In this case, we are seeing that like we are finding, or we are checking if the LLM is highlighting any shift in any shift in the like content. For instance, like as we can see here, there is an expansion of topics. So we call that a semantic change.
Okay, but that's an example. I mean, it's better you have a formal definition of, so that's, you know, that can be used for determine the ground truth.
Okay.
Yeah, and on another slide, so this is tied to another question. In slide number 20, you show the content and the structure. So to me, the content changes, you know, it makes more sense to classify the content change as a semantic change. The structure change, how does the structure change, you know, fall into a semantic change?
Yeah. Well, in this case, the LLM is able not only to analyze that shift in the content, for instance, which it was like what we were trying to capture here, but it also highlights some other type of things. For instance, is something changed in the header? Like we can see here, like this is an example. So there are a couple of more stuff that are changing as well. For instance, what is El Niño? This is the header, for instance, like supporting decision appear here, but it doesn't appear here. So we were calling that a structure. So
Okay.
the LLM was able to.
But do you also call that a semantic change?
No, we don't call it a semantic change for this case. It was like if the LLM is able to say that this change it was here in 2016, but it was not there in 2020.
Right. Okay. So maybe you can make the scope more clear. Otherwise, yeah, I was a little bit confused because you talk about semantic change, but now I talk about a structure change with non-semantic.
Right. All right. Thank you, Dr. Wu.
Yeah. The third question is, how well does LLM detect the changes? Do you have a formal evaluation, like a comparison between the GPT and the ground truth?
In this case, I say here, we were checking that, and it was our early exploration, checking that using human evaluation. We were checking that this answer, which this is just one part of the answer, but we were checking that this answer corresponds to what was happening in the real context. So we were checking that. It was like I say, our early exploration. However, we are thinking about like moving forward to any like automated process for this. We're thinking that maybe that similarity, maybe having like a summary of the changes as a ground truth, and then from the answer compare them like using that similarity. But this is still something we are thinking about for future work.
Okay, sounds good. Thank you.
All right, thank you, Dr. Wu.
Other question, comments for John? So if you could go back to slide 8, please. What Dr. Wu was saying on that sort of drew my attention, right? So I don't know if this is like an animated image or, you know, a carousel or something, but the image itself is different, right?
Yeah, right.
So is there a possibility, I mean, I know this is on text, right? But is there a possibility that the semantic change is encoded in the image itself?
Yeah, absolutely. And that's part of our future work. While we put it
Okay.
here, I think it's right here, because right now, when we think about retrieval augmented generation, we can think about multimodal models. So we could add that to analyze not only the text, but also we can describe the image or maybe analyze the image itself, and then try to see if the LLM is able to say like the image before was different than the image in 2020.
Right. Right. Well, yeah, not just different, right, but different in a semantic way, right? So, all right. So you mentioned it, right? I mean, one limitation, right, is this operates on work files, which are difficult and or expensive to get, right? You can't just get arbitrary work files from the Internet Archive. But this really suggests perhaps that this can be run as an archive level service, right? Instead of a third party that operates on Internet Archive's data. I mean, maybe, you know, you pilot it, do a demo system of it separate, but in a perfect world, this would run on you know, archive side, if you will. But this also made me think, certainly other work that we've done in this group is examined that you need to render the page and have the JavaScript build out the DOM before you can really understand what's there. And what I understood from what you showed is that we haven't done that here, right? This is just on the work files themselves, not the rendered, or is that, which one is it?
Well, no, this is only the word I was showing. It was only on the WAR file. However, moving forward on this one, when we build our own RAG pipeline, we are like crawling the content, but we are also using the content. We are not focusing on like if render or not. We are only just like from the Internet Archive, we crawl the content and we store it as a wet file.
Okay, all right.
But maybe Leslie can chime in, because I think she's the one that actually generated the work files. But I think they were basically crawled using Hypercane, Sean's tool, and that I think renders and then generates the work file from the rendered memento.
All right. So there was rendering involved at some point, right?
Okay.
I believe so.
Right. So yeah, and I think Matt's saying here, right? So you can imagine for these kinds of pages, that they're probably server side, but if we were doing social media pages, you'd actually have to render them before you got to anything, right?
So if I may jump in, I just joined. I'm not sure if Hypercane is storing the post-rendered stuff. What it does, it executes a browser. So that basically means the necessary material is off obtained. So when it replayed, it will likely render better. But the HTML itself may not contain the content you're looking for. If you want to go that route, there are tools like single file that you can use. The name of that tool is single file. And what it does is it does rendition like archive.today style thing.
Right.
So it will download the page, all the page requisites that are necessary, will execute the JavaScript, let the page kind of settle down, and then it will freeze it, remove all the unused CSS. It will remove all the JavaScript at that point, and will store the HTML and all the images and other external resources that are needed. It converts them into data URLs, so they are serialized and put in it. And if you use that and then use an HTML parser on top of that, like Beautiful Soup or something like that, you will perhaps have a lot more, human intended content than any other way. And you can perhaps do it, run it on the live side as well as on the archived pages as well. You can create a single file from a Wayback Machine link or something.
Right. So that's interesting. I didn't know about that. The last question I had, John, was so I mean this thing began with Kritika talking about redirects, and probably not a big part of this particular data set, but if certain pages are redirecting to other pages and not just canonical, dub or not, but if they're redirecting to different paths or even different domains, would you have to follow those redirects down to detect the changes?
Well, that's an interesting question. I didn't think about that. However, I think that's something I can check, because from this specific work, at least for this one, like we relies on the CDX API, on the CDX data, so we got like the specific URL, and when we go to the URL, or like for this specific case, I saw that we got like the web page we were looking for. But that's a specific case I don't know about yet, but I definitely can check it out.
All right. Any other questions, comments for John? All right. So I'd like to thank John. I'd like to thank all of our presenters. But then I've also noticed that we lost one of our alumni. Govinda had to go, but we gained two more here. So we have Dr. Kelly and Dr. Alam. Dr. Kelly, you want to introduce yourself?
Sure, yeah. So I'm Matt Kelly. I'm a 2019 graduate of WSDL. My advisor was Dr. Weigel with Dr. Nelson. I'm currently an assistant professor at Drexel University in Philadelphia. My research topic was mainly about aggregating private and personal web archives. So a lot of the stuff that wasn't typically archived, and go about doing so, and how you go about handling that in the context of privacy and personalization, PII, that kind of stuff, and doing so, at scale. So since being at Drexel, I've kind of looked into the personalization aspect a little more, as well as researched some aspects of semantic evolution over time, some distributed system stuff, really expanding out my research area.
All right, thank you, Dr. Alam.
Hi, I'm Saud Alam. I work with the Internet Archive. I'm the research lead of the Wayback Machine. Graduated from Old Dominion University in 2020. The Zoom presentation era, basically. Yeah. And I hope a lot of people here will cite my work while I was at ODU, and I still kind of work with some of you, continue to work with you guys. And I just heard I might end up mentoring some of you. I'm not going to name the number here, under Google Summer of Code if you applied for that, right? And Internet Archive continues to mentor Google Summer of Code students the last several years. I've been mentoring like 3-4 years. This time, again, we got a few. The formal announcement will happen tomorrow, I think, publicly. So wait until then. Other than that, I am actively working with Dr. Wu here, Michael, Michelle, obviously, and Matt Kelly. So that's me.
All right, excellent.
Anything Wayback Machine, Internet Archive, reach out to me.
All right, yes. Sood is our secret weapon, our man in Paris, as we say. Yeah, it's great. Even though he's working in the Internet Archive, he's still local here in Norfolk. So you can take him out to lunch and pry him with
There you go.
pizza, no pineapple, of course, right?
Yeah, that is a better way to say it, I guess. Yeah.
All right. So again, thank you to everyone who presented, took the time to show up. We really appreciate it. It's great to keep this going. Any last words from other faculty, WSDL members? Remember, WSDL's for life. So. All right.
I will see some of you in New Jersey next the week after next week, I guess, for Web Science Conference.
Oh, right, for the Web Science Conference, right?
Yeah.
Yep.
Yeah.
Absolutely. Yep. All right. Again, thanks to everybody. Really appreciate it. Very successful. And we'll have this video out and posted, of course, in the blog, hopefully very soon. All right. Thanks, y'all. Bye.